present today María Díaz García. So you know that the seminars that we have are very heterogeneous in very different topics. So today we are going to talk about molecular materials for optoelectronics, which is something that we are very much interested in here. So many of you know Maria already from her work. She's been very active in the field of optoelectronics, and particularly in organic lasers. So actually, Maria comes from this university. So she did a PhD here, and her degree too. And she was working with nonlinear optics, right, during your PhD. Then she moved to United States, and she was working as a postdoc in the group of Alan Higer, who received the Nobel Prize in 2000 for the discovery of the conductivity in polyacetylene. There, she was a member of a team where they pioneered the discovery of optical gain in semiconducting polymers. Okay, from there on, there was a large activity towards the development of the field of organic lasers based on conjugated materials. Then she carried on with another postdoc in the group of Professor Morner in California too. In another California Davis?
No, UCSD.
California is
yes.
Like California.
Yes.
And then she was also working with another Nobel Prize with Professor Morner, received the Nobel Prize in 2014, working with photorefractive polymers. And she moved to the University of Alicante. She's full professor there. And she's basically the founder of the organic laser team there in Alicante. She has many collaborations. We have many topics which are of interest for both of us. So I'm very happy. I'm very looking forward to your talk. You can start whenever you like.
Okay. Thank you very much. First of all, I'd like to acknowledge Juan and all the people here for inviting me to come here to the Universidad Autónoma, which is my home in a way. So today I'm going to discuss generally the topic in which I've been working for quite a few years already, and the title is All Solution Process Organic Lasers. So this is in the context of plastic optoelectronics, meaning by that optoelectronics based on organic compounds or active organic compounds. And the major interest of this kind of materials for optoelectronics is based on the chemical versatility offered by the synthesis. So it enables to tune the properties of the materials. Besides, in case of materials that are soluble, they can be processed easily as thin films. So this brings the possibility to prepare devices at a low cost that are mechanically flexible and also that can be easily integrable with other devices. So there's a whole range of devices, including solar cells, light emitting diodes, or field effect transistors that are made with this kind of materials. And there are some of these applications that are today already in the market, such as, for example, the OLEDs. Here I'm going to talk about a device not included before, is the laser. And before starting, let me remind briefly what a laser is. Laser is the acronym of light amplification by stimulated emission or radiation. Basically, it's a light source that has a very high degree of coherence and directionality. And the main requirements to have such a device is first to have a material that is capable of amplifying light by a macroscopic mechanism that is called stimulated emission. So basically, the idea is that if you have an electron that is in excited state, so this electron can be released to the fundamental state stimulated by another photon. So because of that, this emitted photon is in phase with the stimulated one, and this is the key for this coherence property. So the fact that you have this material provides gain, this brings the idea that if you're able to have this light going fast, go several times through the active medium, this provides larger gain. So this is the reason mainly for the resonator. So the basic resonator would be a couple of mirrors. So you can place the active material between the two mirrors. So the light can travel many times through the active medium, and then you can get amplification. Besides, also, this resonator is the reason why you can have directionality of the beam. The other requirement you have is to have an excitation mechanism. That is, you need in some way to put these electrons in the excited state, and you can do that by different ways, mainly electrically or optically. So, in fact, in order to have this population inversion, this means to have many electrons in the excited state. You cannot do that with only with 2 levels, and you need 3 or 4 levels involved in this process. So in this way, you can efficiently have more electrons in the excited state. In fact, you cannot have such a population inversion with just 2 levels. With this idea in mind, organic molecules are very good candidates, very good active materials for such purpose, because they are very good for having such 4-level systems. And besides, because they have vibrations, the molecules vibrate, they have different levels. You have a very broad PL spectrum, and this combined with the large variety of dyes that are available, you can tune. This provides a large tuning range, so you can have a laser source that can be indivisible, and you can adjust it very easily. In fact, this is one of the main attractive points of organic lasers. That is the possibility to have a laser source indivisible and to tune the wavelength with great detail. From a historic perspective, dye lasers in liquid solution, in fact, they were already demonstrated many years ago, and in fact, they were commercialized. And they've been used in medicine, for example, for stain removal or for skin vascular lesions, mainly because you can adjust very easily the wavelength of the emission. However, these systems are large, dirty, and they need additional large pumping sources. So already since many years ago, there was lots of interest in trying to insert these molecules in solid matrices, basically prepared as rods. And there, the main problem was the photostability, because once you have these dyes in a matrix, the photostability was poor. So most of the efforts were trying to improve, were devoted to trying to improve this property. The situation changed in 1996 when stimulated emission was discovered in semiconducting polymers. And the main motivation was that these materials brought out the possibility to using electrical pump. At that point, since then to today, there's been a great amount of work done in the field, most efforts focusing in trying to reduce the threshold with this idea of at some point using electrical injection. And the situation is that today, a direct electrical pump has not been demonstrated. However, what has been done is to be able to pump these lasers with latter-emitting diodes. In fact, there has been a very recent work of the group of Professor Samuel, in which they achieved, it's not direct electrical pump, but it's like pumping with light-emitting diodes that are integrated in the same system. So this means that although initially it seemed that the main motivation was to be able to fabricate an electrically pumped device, because the threshold was reduced so much, it means that optically pumped structures are interesting by themselves. And with this idea in mind, and with this context, which is where I've been working for many years, I'm going to focus in what I would call the thin film plastic lasers. So the idea, compared to the traditional, let's say, kind of laser in the 90s, the fact that you're using a material, it can be semiconducting or not, because in the end, we're not going to use this property. The idea is that you can prepare it as an active film, and the kind of resonator that you're going to use is not these two mirrors, but a kind of structure that is called distributed feedback. Basically, this resonator is a grating, it's a diffractive grating. This is the standard configuration. That is that you have an inorganic substrate where for some method, you can be able to prepare a corrugation in the substrate. It's a diffractive grating. And then you deposit on top of that the active film. This is what I call the standard configuration. And there are other configurations in which, and this is important, the resonator is made in plastic with a plastic material. This means a polymer. So when I say in my title, all plastic, all solution process, means that the kind of resonator that we have been using, mainly recently, is a device where the resonator is also made in a polymer. In fact, I'm going to focus, I will describe more things later about this kind of configuration where you have your substrate, your film, and then your resonator located on top, also fabricated in a polymer. Okay, let me briefly explain what an organic distributed feedback laser is. Basically, it's a waveguide that includes a relief grating. So there is a modulation in the gain or an interfractive index. In fact, the grating plays two roles. The first role is to provide this feedback that we were talking about at the beginning, the feedback of the light. So this, for the propagation of the light in the plane, what you want is to get feedback so you can reinforce one of the wavelengths. And one of the wavelengths that you're reinforcing is the one that complies with this equation. This is a wavelength. And this is proportional to the refractive index, to the effective index, sorry, which is something that depends on the refractive index of the various mediums involved, also the wavelength and the thickness of the layer. And this is the grating period, which is the separation of the ridges of this wave. So this is the first mechanism to provide this feedback, but there is another role of this grating, and it's to extract the light out of the device. In this case, the grating acts as a structure of the light, and for the case of second-order devices, that means m equals 2 in that equation, the maximum intensity occurs perpendicularly to the film. So this kind of device is particularly interesting for applications for sensing, where you have your emission perpendicular. So in fact, these kind of devices, now I'm focusing on organic DFB lasers, have already demonstrated applicability in different areas, such as spectroscopy, optical communication, sensing. And despite all these efforts, there's still major challenges remaining to really bring these devices to the market. From the point of view of the active laser material, although there's been lots of advances, there's still the need to find a material that is simultaneously that has a good performance simultaneously in various aspects, such as the high photostability, a low threshold. This means the energy that you need to operate, to be capable to emit in different colors, and also to be processed from a solution. Trying to have a device where you can have these advantages we were discussing at the beginning of low cost, mechanical flexibility, and so on. Also, from the point of view of the laser resonator, there's been lots of work done, but the best performing devices reported normally have been based on gratings that were engraved on inorganic substrates, sometimes with very sophisticated techniques. So when you want to use resonators where are made in polymers and using techniques that are simpler or at a lower cost, normally the performance goes down. So again, there's a great challenge trying to fabricate resonators with a method that allows you to obtain still this very high performance of the materials. 'So with all this in mind, the work in my group has focused on trying to improve these devices, focusing in different aspects. On the one hand, we have been working on the resonator. In previous years, we were preparing devices with, okay, this is like the standard configuration with inorganic substrate, fabricating these gratings with non-imprint lithography. Also with this one where you imprint the grating on the active film. Then we developed a method in our lab using holographic lithography. Initially, we were putting this grating below the active film, but then lately, in the last years, we're focusing on this later geometry where we have our resonator located on top. It's what we call the top layer resonator geometry. And as I'll show you later, this offers several advantages with respect to the others. And of course, the point is that both resonator and active film are prepared from solution-based methods. By now, this is inorganic substrate, but okay, this is easily can be replaced for another organic polymeric substrate. So to prepare a really completely polymeric device. This is in relation to the resonator. We have also worked in trying to improve the active material, and in that part, we have collaborated with lots of organic chemists, in which sometimes the major novelty comes from the point of view of the material. Sometimes the synthesis of the compounds are really challenging. And what we have obtained very interesting results in materials, very novel materials. We have studied semiconducting polymers, or which is what we have done most, dyes dispersed in inner polymers. Basically, the idea is that when you have, taking into account that you're not going to use the semiconducting property, going back to these dyes dispersed in inner polymers allows you to have a higher photostability, which is one of the problems when you're using semiconducting polymers. Also, we have done some work in relation to applications, because the idea is that, as I said before, in this equation, as you can see here, the wavelength of the emission depends on the effective index. So if you change the effective index in some way, maybe changing the refractive index of the different layers or the thickness, you can change the wavelength. So taking this in mind, the idea is that if you use this device, in this case, we're pumping from below, you put on top of that a drop of water, for example, or some kind of compound. What happens is that you're changing your refractive index, and because of that, you are shifting the wavelength of the laser, the color of the laser. So by looking at how much this peak has shifted, you can detect, in this case, the refractive index of what you're putting on top of that. That would be like the first simple demonstration, but more interesting is if you can detect something interesting. In this case, we did this work where we demonstrated a sensor to detect a protein, this Dpto protein. This protein is related with different types of cancers. And in this case, in order to make the sensor specific for this protein, what we did is to functionalize the polystyrene surface with the anti-protein. And then we were able to demonstrate that indeed this works. So this is something we did 2 years ago. Now we're trying to do, well, we are already doing this, but instead of using this is the standard device with the grating engraved on the substrate, in inorganic substrate, we're trying to do these things with these devices, these kind of devices. Okay, and these are some of the results also at the end. So I said, these are examples of work done in our group. In 1907, this is the first publication where we presented this kind of geometry and the process to fabricate this kind of device and compare it to the standard geometry. I'll discuss this in detail. And also, well, we have studied many different materials. For many years, we have focused in many different derivatives of the family of purlines. Also, we investigated some oligophenylene vanillines, this kind of oligomers, where we had a collaboration with the Professor Eiichi Nakamura in Tokyo University. And they synthesized these molecules where the key was to put these carbon locks here, so they prevented the molecule from twisting, and because of that, these molecules had a very high field efficiency. Also, in the last years, we've been focusing mainly in nanographene. I'm not showing anything here because these are the examples I'm going to show you here are precisely of this family of nanographenes. That this is a work that we're doing now with Professor Ji Sang-gu at the University of Singapore, which is an excellent group of organic chemists that we're getting very, very nice studies in collaboration with them. So before moving on, let me go to some to explain some of the experimental methods that we are using. Let's say first we prepare the film, the devices. The devices are active film. This is a photoresist this is the starting material to fabricate this resonator. They are prepared by spin coating from solution. And an important aspect is simple, but it's important that this one is prepared from an organic solvent, and this one is soluble in water. So because of that, when you prepare this resist on top of the active film, it doesn't get distorted. There's some other people trying to use this kind of geometry with other kind of resist, but the problem is that sometimes the quality of the material gets worse when you put the resonator on top. So in our case, we don't have any problem. So the properties of this layer keep perfect. Okay, so to fabricate the grating, what you use is a process. This is to fabricate the diffractive grating. We use holographic lithography. So the idea is that we expose the gelatin. The gelatin is gelatin with is dichromated, and then what you do is you illuminate with the interference of two beams. So you're illuminating with this kind of pattern. And then the idea is that in the areas that are illuminated, the chromium 6 plus changes to chromium 3 plus. And because of that, the material gets hardened. So this means that you are transferring this illumination pattern to a hardening pattern in the gelatin. Then you desensitize, you eliminate the remaining chromium 6 plus that didn't react in the areas that are not illuminated. And then what you do is that you develop with an oxygen plasma. With this treatment, which is very simple, it's like a couple of minutes, you are just getting rid of the areas that have not been illuminated, and then it's very soft. So in the end, you're getting this kind of structure. It's like this one-dimensional grating. And okay, so this is in terms of the cavity. Before explaining the kind of the setup to characterize the properties, let me explain briefly a mechanism what is called amplified spontaneous emission, which is, I mean, if you want to assess the capability of a given material to be used for lasing before putting the cavity, what you do is to try to identify what is called amplified spontaneous emission. Amplified spontaneous emission is a type of emission where you have a moderate directionality and also an only reduced coherence, because in fact it's a mixture of amplified spontaneous emission and stimulated emission. And because you don't have a cavity, you don't have real lasing. Okay, so when you have a stimulated emission, you get some gain, so you can see a narrowing of the spectrum, and this is normally, in order to do that, you need to have the light confined for some time, and this is precisely what you get when you have a waveguide. So our films, this is the typical structure, no resonator, just our film over substrate. You need to have a waveguide in order to have amplified spontaneous emission. So normally what you do when you have a material, before you put the resonator, you characterize this property, the amplified spontaneous emission, to see how good the material is. And of course, it's very important. We did lots of work in the past trying to optimize the waveguide, the propagation of the light in the waveguide, in order to next go for and prepare the device. It's important to have this part optimized in order to get later the best results, the possible results with your lasers. For the characterization, either the amplified spontaneous emission or the DFB characterization, the laser characterization. What we do is we excite our device with a nanosecond, in our case, a pulse source. In our case, we're using nanosecond pulses, either with a beam of light using a cylindrical lens or with a spot of light using a circular lens. And then in this case, for the ASC, we're getting the light emitted from the edge. And in this case, in the case of DFB, we're collecting the light in perpendicular direction. Okay, so how do you know you're getting lasing or ASC? You see a narrowing of the spectrum at a given intensity, the threshold. Besides, you see a drastic increase of the emission intensity at a certain intensity, the threshold. You also can see, you can determine the gain. You plot the intensity versus the length of the stripe in the case of ASC. And also you can characterize the photostability. Okay, basically, the photostability is to look at the intensity under constant pump, and then you see how it decays with time. Okay, so these are normally the properties that you characterize when you characterize this. And it's, additionally, sometimes we have done some work trying to understand the photophysics of the materials. For that purpose, we've been doing, in this case, in collaboration with Professor Lanzani in Milano, doing time-resolved photoluminescence spectra and also ultrafast transient absorption. So here the idea is to try to see how the transmittance of the beam changes upon a probe. Okay, so doing that, you can determine different processes such as photobleaching, stimulated emission, or excited state absorption, trying to understand macroscopically what's going on or why one material is working in one way or another. So let me start then showing some examples of things that we've been doing, starting with the resonator. As I said, this was a work published in 2017. We proposed this structure, as I said before, with this dichromated gelatin resonators on top of the device. And then we, with a lot of care, we made a comparison of this structure compared to the standard one and to the other one. Having in mind that today, most of the devices of this kind with the resonator on polymeric materials have normally like one order of magnitude or more lower performance than the standard configuration. Okay. So in this case, we use very good performing materials. This Perlin, this is commercial one, and these are these carbon-rich oligophenylene vinylanes. And what we observe here, these are devices prepared with either the top resonator geometry. These are all with this geometry, emitting in different wavelengths depending on the compound. And what we observed is that the thresholds were the same as the standard configuration, which in itself, it was a great major result because, as I said, normally it was worse. And an interesting is what I'm saying here, similar to the standard configuration, but an interesting advantage of this configuration is that the efficiency, this means the slope of this curve, when you're plotting the emission intensity versus the pump intensity, for the top resonator geometry was better than the standard one or the other one. And this is because the fact that you're having your resonator on top is improving this property of extracting the light out of the device, which is one of the roles, two roles. One is the feedbacking plane, and also the other one is to extract the light. So when you have the resonator on top, this role is better. Another interesting thing is that of this kind of device is that here the thickness of the film is uniform. Okay, so it's uniform across the whole device. So what we did also, thanks to the fact that we're using holographic lithography, which you can prepare samples of several centimeters, we prepared a sample where we divided in several sections. In each section, we had a different rating period. So we were able to have in the same device, we were able to tune the emission wavelength in this range, just by moving the area of the device where we were excited. And this is important because normally when you tune the emission wavelength, what you can do is either you change the material, but then it's a different sample, or you change the thickness, but then it's a different sample, or people sometimes have used like what is called the wedge configuration, where you can prepare a thin film that has a varying thickness across the film. But all these, the problem is that the threshold is not the same when you change the color. So in this case, because of the kind of device we have, we were able to obtain low thresholds in most of the colors. So that was also a very interesting aspect of this kind of device. Well, later on, this was later, that was the first work. Then what we did is trying to optimize the fabrication, trying to see what was the influence of changing the device parameters, such as the grating depth, the residual layer. You know, normally you can have this layer or not, trying to see which was the best parameters. And so in the end, well, I don't want to get into all the details, but we did many experiments with different residual layers. We're changing this layer, also changing the depth of this D. And what we observe, as you can see here, these are the ones. This we are putting the laser threshold and looking at the efficiency. And these dotted lines correspond to the points where there is no residual layer. So in the end, what we observed is that the best results were obtained, the lowest thresholds were obtained when there was no residual layer. So then, if you take the points where you only have, if you don't have a residual layer, then you can try to think what is the best depth. It's better to have a depth of 100 nanometers, 180 nanometers, the depth of the grating. And what we observe here, if you're looking at these graphs, what you see is that, well, this is the threshold and this is the laser efficiency. And what you see, and this is the grating depth. And what you see is that when you increase the grating efficiency, the grating depth, sorry, what you see is that the threshold increases. And on the other hand, you are improving the laser efficiency. This means there is a trade-off between the two properties. And this is because, as I said before, the grating plays two roles. One is to provide feedback, okay, and the other one is to start the light. So what happens if you increase the depth? What happens is that the threshold gets worse because then it has more losses because the grating depth is very large. Okay, and on the other hand, you're improving the property of extracting the light. So with this kind of system, it's not possible to optimize both at the same time. Okay? In this case, we decided, okay, taking into account this trade-off, a reasonable value would be 100 nanometers, because then you can get good threshold and already quite a reasonable efficiency. There's been in the literature people that has tried to improve these two properties separately, for example, using mixed order ratings or other kind of things. Okay, but at this point, when we finish this, the nice thing of this work is that I'm not going to explain this because then it could take me quite a long time. But the point is that nowadays we're able to fabricate these devices with a great control of the properties, the final properties of the device, controlling the fabrication parameters. Okay, so another thing we did later is, okay, these first lasers we fabricated, they were all emitting in the green, orange. And of course, if you want to go to lower wavelengths to fabricate devices emitting in the blue, you need to prepare devices with smaller grating periods. Okay. So in this case, we said, okay, let's see how small can we do these grating periods. Let's see if we have limitations in the resolution, because the point is that if you fabricate, these are in the previous devices, normally the grating periods were 250, 60, 300. Okay. So the point is that, okay, let's try to make smaller rating periods, and particularly these are the values normally you need for blue emitting materials. And what we observed is that we didn't have limitations down to periods of 200 nanometers. Okay, and well, in this work, this was published a few years ago, we also investigated, well, we did some things related to the profile. It was sinusoidal or more like kind of a square. I'm not going to go into details, but the point is that we were able to see that indeed we were able to fabricate these devices with low rating periods, and then we took a bunch of tiles. In this case, they were copies with different substituents here. That some of them were so novel that they were all emitting in the blue. So we were able to fabricate devices going from 360 to 460 nanometers, choosing these correspond to different derivatives. And some of them had photostabilities that were improved with respect to previous ones. Okay. So let me move now to tell you some examples about materials. So now, considering in all these studies I'm going to show you now, I'm going to use this top layer device that I was discussing before, and then I'm going to focus on the material, on the active compound. So in the last years, we have started investigating nanographene. This means small molecules, small pieces of graphene. And of course, there's been lots of work done with graphene, but when we talk about graphene, it's more like a macroscopic graphene. And the approach here is to use compounds that are synthesized chemically. And for all this, of course, this has been possible because of the collaboration with Professor Jisan Gu. And the idea is that when you have graphene, this is like a layer of graphene, there are different possible types of edge when you select a piece of graphene. For example, this one, okay, or this one. These are different possible molecules that you can have. And the idea is that you can have basically two types of edges. This is what is called the armchair edge. It's like an armchair, or you have the zigzag, which is like this. So this is important because the optoelectronic properties depend a lot on the type of edge. Basically, if you want to do for optoelectronics, if you want to have light emission, it's good to have zigzag edges. Okay. But on the other hand, the problem of these edges is that they are very reactive. So normally when you prepare molecules with zigzag edges, they are not very stable. So a very challenge for chemists is to prepare the molecules with substituents in different positions, first to prevent reactivity, to make them stable, and also to prevent that the molecules get interfere with the others, or to get you get a concentration, what is called the concentration wanting. If you have many molecules, they get aggregated, and then you lose the photoluminescence. Okay, so at this point, this was in the first report on the first spontaneous emission on this kind of materials was by the group of Paterno and Lansani. This was in 1997, but it was just ASC. So at this point, we faced this problem. We investigated the properties of these three derivatives prepared by Professor Jisan Gu. And as you can see, these substituents here provided this property that I said to provide solubility, to make the material stable, and also to prevent in some way aggregation. But it's true that normally the concentration of these molecules in the polymer are very low, on the order of 1% or 2%. Okay, so this is something that maybe can be improved further. So as you can see here, we have these three materials. Let's see, 1, 2, and 3 emitting in different regions of the spectrum, and we observe ASC in all of them. And also, we made DFB lasers. These were the first DFB lasers done with nanographenes. And as you can see here, with the 3 different compounds, and then the different peaks correspond to different devices with different rating periods. Okay, so we were able to prepare different, and as you can see here, the width of these peaks is very narrow. It's below the nanometer. Of course, with this top layer polymeric architecture that I was describing before. Importantly, the thresholds of the materials were very low, were among the best materials that we investigated previously. And probably one of the most important results was the excellent operational lifetime. The excellent, I'm meaning, okay, we were pumping for, let's say, 10 to the 4th here, and we specifically for the larger compound, we didn't see any degradation. So that was a very important point. Later on, we did this work. This was another very interesting work from the point of view of chemistry. So this is the series I just described. So when you use the conjugation, you see the emission. And at some point, we had these other compounds that you see, in fact, they are in a way similar to the others, but the idea is that here you are studying the conjugation, let's say in 2D, okay, because it's extended and these molecules are more in 2 dimensions, why it's extended the conjugation in 2 dimensions. And the idea is that, is it better to extend the conjugation in 2 dimensions or in 1 dimension? So the idea is that we have these molecules where we extending the conjugation in 1 dimension. So the number of pi electrons that you increase when you move from this one to this one or to this one is 8 pi electrons. When you go in this direction, you increase 6 pi electrons in each step. Okay, so that was the point. Is it better one or another? And what we observe with this very aceno-acen, the TTR and BTR, is that the emissions were shifted further to the infrared. So this was an important, what I'm saying here is more effective resist with a smaller conjugation increase. This means that instead we have 6 electrons when you move in each step. In the other case, you had 8 electrons, and here we were able to reach towards the infrared, much farther wavelengths than before. Okay, so we have these 2 compounds. And this one, we also observe an interesting thing is that we observe what is called dual ASE. We observe ASE at 2 different positions, not at just 1, but 2. At this one and at this one. Okay. And in this case, we performed in collaboration with Dano. Well, this was Rafael Muñoz, it was his PhD. So he did some transient absorption, trying to understand why basically understand why this dual ASE. And the point is, the reason for that is that there is, you can see this excited state absorption, which is a mechanism, a loss mechanism, that appear in this region, which is the region where normally you have the emission. Normally, something I didn't say, normally when you have ASE, for example, in this one, ASE occurs normally corresponding to not to the main PL peak, because this is very close to the absorption. So you have very large self-absorption, but in the first vibronic peak. This is the most common thing in many materials. In this case, you can see that you have, this could be like the typical one in the sense that it appears here, okay, in the first vibrational peak, okay. This is the absorption, this is the photoluminescence, but we have the other one that appears here. And the reason for that is that in this region, where normally you have the ASE, there is some excited state absorption band that makes the losses are very large. So the point is that normally you don't see this peak. It doesn't mean that it's in every material, but even if it's there, if the losses are very large, because this is very close to the absorption, the threshold would be very large. And then you get emission normal in this one. But then if you have a loss mechanism in this area, what happens is that in the end, the threshold for observing this one is very similar to observing the other. So in fact, you see ASC, the dual ASC, sorry, because in fact, this is not it's not a good thing in the sense that you have more losses, and then you're observing both just because you have more losses here. And in fact, the thresholds are larger than normal. Okay. So we also make DFBs with these devices. These are with the TTR and these are with PPR. We made devices with both peaks, right? With the one, the two. Okay. Well, and another thing that I didn't mention, I think it's here, but I forgot, but I think it's very interesting that, as I said, it's more effective. This strategy of extending in 1D is more effective in shifting the emission to the infrared. And this is because, this was also done with some calculations. This is because the localization in this device, in these materials is more in the edge, while in the others is more, because you're standing in 2D, the electronic cloud is localized in the whole molecule, while in this case it's more in the edge. And this is why you are able to shift more to the infrared. So this is a very important thing from the point of view of chemists, because a very interesting point is try to develop molecules that emit in the near infrared, because there are not so many materials that emit near infrared light. So there are lots of work done in chemistry trying to prepare these molecules. So I think this was something very important that we learned from this to design new approaches to synthesize molecules emitting in the infrared. Okay. Well, more recently, also with this kind of nanographene with emissions in the near infrared, we investigated this triangulate dimer. This is a fused triangulate. This is a triangulate. Okay. This is a fused dimer. Okay, because you have this one with this one fused with this one. And then these substituents are substituents to increase the solubility and all. And as you can see here, this material, this is absorption, photoluminescence, this is the photoluminescence, and this is the photoluminescence. You have this absorption here, you have these two bands here. And as you can see here, we were able to obtain emission even further in the infrared. Here we're getting like 77 ASC. And again, we fabricated devices emitting at different wavelengths with our. And well, from the point of view of chemistry, an important novelty in this work was in fact the way they prepared this compound, because they were able to do it in a simpler way, because normally the synthesis of these compounds sometimes is quite difficult. And they propose, I'm not talking about the synthesis, of course, because I'm a physicist, I'm not a chemist, but the process to prepare the compound was very efficient and much simpler than others. Okay. And yeah, the last part, let me show you, moving to kind of the application of this kind of devices. As I said, one interesting or possible application of these devices is to use them as sensors. Okay. Similarly to what I showed you before with this work that we did in 2015 with the resonator below. So now we're trying to see if we can use these devices, the ones with the resonator on top, to make sensors. Okay, so now this is something that we're just finishing now. The first step is to demonstrate the capability to use it as a refractive index sensor. Okay, so this has been quite difficult. We have quite some problems, okay, because at the beginning the problem is that this water, you put the water on top of that, then you're trying to see the seed of the emission, but at the beginning we have problems because the water penetrated in the gelatin, although the gelatin, once it's hardened with this oxygen treatment, it becomes very hard. So normally it's very stable. But when you're doing these experiments, it's a very small effect, but you can see. Okay, the problem is that some part of the water gets into the grating, so you see some movements of the peaks. But we have improved that by doing some fabrication, but it has taken us a long time. But now we've been able to see or demonstrate the possibility of use this as a refractive index sensor. As I said again, this is the Bragg wavelength, and it depends on the effective index. This is what we're changing when we're putting a layer of water here, water or glycerin, and this is what we're doing here. We're looking how much this peak moves when you put water, different glycerin solutions, and this is a solvent. We did this experiment with a solvent. This is tetrahydrochloroxane, and the reason for doing that is because we also were doing some kind of calculations, okay, to predict where the peaks should be, and they were not exactly in the same place. And I think it's because the water penetrates a little bit, and this was just to see using a solvent that is not water, that with this solvent doesn't penetrate. But anyway, we saw that we obtained this was done with 100 nanometer 80. This is the thickness of the film. And then we also prepare devices with other thickness, and the best sensibility, the sensor sensitivity, which is determined by plotting the shift of the peak, this distance versus the refractive index. And then you can get the sensitivity here. We were getting sensibilities, and then you can see that with the thinnest film, you can get the best sensibility. This is expected normally. And well, I'm not showing it here, but another interesting thing that we've seen, this is done with the TE mode, but we have done also, we have observed, this is the T mode, but we also see the TM mode, the transversal magnetic mode of the waveguide, and then you get a better sensitivity when you use the TM mode. Okay. Well, this is something that we're now trying to put together to publish it, but this is not published yet. And of course, the next step is to make a sensor that is useful for something. And we are also, and in this sense, the fact that we're using gelatin, this is very interesting because gelatin is a biopolymer, it's a protein. So we have already done some work trying to functionalize this gelatin, and we've been successful. Still trying to functionalize it with something interesting, but also gelatin is used a lot in medicine and bio applications because it's biocompatible and all that. Well, and that's all. This is just as a summary. I would say that I'll show you some examples of the things that we've done, trying to improve the resonator. We demonstrated, we've seen that this top layer polymeric DFB resonator is very efficient. So we're able to tailor threshold, have photostability, have efficiency, wavelength tunability, etc. From the point of view of materials, I'll show you some examples of novel nanographene where this has been possible. The merit has become mainly from the chemists that are able to synthesize all these molecules that are really, it's a really challenging synthesis. That is why they have been published. Many of them have been published in Alicante, because the chemical synthesis is by itself very, very, very novel. And also from the point of view of applications, we are now trying to use this for something useful. I mean, there's lots of things done with sensing with DFBs, but so far not many using this kind of resonators and not with the resonator on top. So we believe that this is something that we still can. Well, last but not least, I'd like to acknowledge all the people in my group, the University of Alicante, myself, Professor Villalvilla, Pedro Boja, and then my previous PhDs that I was showing most of the work, Rafael Muñoz Mármol and Dpto Bonal, and at present I have 2 PhD students and also, of course, all the collaborations that we have in different aspects of all the things that we do, and of course, fun. And well, of course, thank you for your attention.
Yeah. Okay, so time for questions. Anto?
Very important problem of the organic lasers is the stability. You want them to work as long as possible to be commercially useful. So with the top layer DFB, I would expect that the advantage, or at least one advantage, is that you protect the active layer against oxygen. So for that reason, I would like to know, is this you said the residual layer is 0 is the best DFB for the threshold, I guess, but what about the stability? Is it not protecting against the oxygen? So is the stability not better than the residual layer is not 0?
Well, thank you very much for the question. I think it's a very good question. And indeed, well, one would expect that this layer would protect. And in fact, with these materials that I was showing before, with the purlins or with the copy-Vs, they are very stable. And with those, we try to see if this layer was improving the photostability or not. And we didn't find really differences. Okay. So it doesn't seem to improve when you have the layer on top. So, however, in other materials, that are not very stable. For example, with TPD. TPD is a molecule that has been used. This is a blue emitting material. This work is not here, but we published a paper also on that. TPD is a material that emits in the blue, and the photostability is quite low. So in that case, we observed that indeed the photostability was improved. Not very much, but was improved in some way when you have this layer on top. So in that case, because I mean, all these optimizations that we were done with the residual layer and all that, they were done with the purlin that was very stable, and with these copy-Vs, and we didn't see an effect of the layer on top. So
what then limits the stability of the purlin-based laser device? If it's not the oxygen, what else is it?
Well, I think basically it's photobleaching of the molecule at some point.
Photobleaching is due to crossing to the single triplet and generation of singlet oxygen, I guess.
Well, exactly the mechanism of degradation of purlin, well, it's not perfectly clear. I mean, degradation is always a very difficult problem, and of course, each material is different. It's true that in organic semiconductors, it's always said, okay, it's the oxygen, and it's true that the oxygen is a problem, but I think with purlins, for example, it's not such, because, for example, with semiconducting polymers, that there's been lots of work done. Many of the studies are performed in a chamber, but you don't have oxygen. So sometimes they don't say, or they are encapsulated. It's true when you have semiconducting polymer, because you have an E film, then the thresholds normally are lower, but the photostability is worse. I mean, I remember the first work done in Santa Barbara with the semiconducting polymers. They lasted for, to do the experiment, but no longer than that. And for example, in the group of 5 for Samuel, that I have a student going there, normally they perform the experiments in a chamber, so there is no oxygen.
That's not useful for applications.
Yeah, but that's, well, you can encapsulate it. It's true. I mean, we've been working quite a lot in photostability, and with purlin, we've done a lot of work, but trying to understand why it degrades in detail is not so easy. That's easy, but the point is that it's true that for the point of view of sensors, for example, in the end, it's not that important because, I mean, of course, if you want to have a laser that is working many hours, it's probably this is not a very useful application because not only because of the degradation, but also because the amount of light that you're getting out of that. These devices are thin films, so the amount of light is very small. So I think that probably these sensing applications are one of the most have more potential because the mechanism of the working principle is the shift in the peak. So well, it's true that you want to have a low threshold, so you don't need like a big pumping source to operate. So you have but in the end, you don't need the laser to be working for many hours. With the Pernis, for example, or with the nanographenes, if you're pumping not very high, let's say you pump 2 times or several times above threshold, it lasts for more than 8 hours under constant pump, which is a lot compared to others. So indeed, the photostability is a major issue, and not only for how long it lasts, but also for trying to make, for example, CW pumping, which is another thing that is important in that. Yes. So, but this is oxygen is not good, and yes, this layer is good for that. So
I wanted to ask you regarding the sensing, the thickness of the grating must also play a role because of the Venetian field has to interact with the analyte. So
yeah.
how thin has the grating to be in order to?
Yeah, well, the thing is that well, in this work that I said that we optimize this one, of course, we were not looking at the sensing. Okay, here when we did this with the residual layer and the depth and all that, here when we say the best results, we were looking at the efficiency and looking at the threshold. Of course, if you want to do it for sensing, this is something we haven't done yet, but we will. So by now, I think that the ones that I was showing the results, I don't remember exactly, but maybe they were 60 nanometers or something like that. It's true that the thinner the thickness or the active film, the sensitivity is better. But we haven't explored yet what is the role of because in that case, maybe for sensing, it's better to have, I don't know. This is something, and also the profile, I mean, or maybe even the residual layer, maybe for sensing, I don't know, it's better to have. I don't think so because, and also it depends because, okay, for refractive index sensing, but if you want to functionalize this and then do sensing of a certain material, I think that is very important, the depth, probably also the type of profile, because I'm drawing this in this way, but in fact, this is not here, but when we did this, you can see here, you can see, in fact, this is not sinusoidal. This is more kind of a square kind of profile.
It's a typical profile that you get when you do this interferometry.
Yeah, but you can also make it more, it depends on it depends a lot on the exposure, and also when you're doing the etching the material with the so it depends a lot on that. So, and again, we have explored this. In fact, it's funny because this optimized fabrication procedure for obtaining the best thresholds and all that resulted in this kind of profile, which in the end is the most effective one. This is, I think there are more details in this paper. We haven't explored in detail, how to change the profile. This is something that we could also do. But
More questions? Yeah. So?
Yeah, absolutely. Yeah. Yeah, my first question is you told that you could measure the gain of the impact lasers, or I don't know if it was the AC.
the ASE.
ASE, yeah. Yeah, in this field, because I was doing this, but there's something I have not clear is the intensity you plot there is the intensity together with the photoluminescence. You subtract and then you integrate all the area in the
No.
peak, or
Normally, when we do this, we take, well, you could take the integration, but normally we take the intensity in the peak, at the peak,
just one wave
at the peak of the ASC.
with the photoluminescence.
Well, with the photoluminescence, with this, when you're doing this experiment, okay, it's photoluminescence, but pumping with you are doing this, and then when you get the ASC, okay, then you take this wavelength, and then you measure the intensity at this wavelength. Of course, at some point, when you are pumping with a small length, because this is done at the constant pump intensity. Here, we're changing when you're doing these experiments, you're changing the pump intensity, well, I'm plotting a spectrum with a low intensity, and also with a pump intensity. And then when you do this experiment, you fix the pump intensity, and then you change the length of the strike. In this case, the change of the length of the strike was, I guess, 3 millimeters or something like that, and then you're changing that. So, for example, if you're in a case where you have the narrow peak and you take an intensity which is above threshold, okay. The problem is that when you start decreasing the length, at some point you don't see stimulated emission anymore, and then you're getting these curves. But in fact, now we're not getting the gain with this method.
Yeah, I know. You
No.
make like
Recently, there's a program. It's Luis Tedran developed a software where it's a software, but it's free use. And then by taking many spectra, ASC spectra, different concentrations, you can put everything together, and then it determines not only the gain, but the losses. And then you plot the gain versus the pump intensity. So you can perform this experiment for many pump intensities, and then you plot the net gain for different pump intensities, because of course this value depends on the pump intensity. And then you can also extrapolate and determine the losses of the waveguide. Well, this is here, but now in fact we're not doing that. We're doing.
The other question is, I don't know, did you try any other periodic structure, like, I don't know, circular circles, I don't know. Yeah, you said yeah.
Yeah, well, in the past we as many people have been doing to the ratings, okay, and I think that in the past we did one paper when we're doing this standard configuration and doing the gratings with nanoprint in collaboration with Techniker. At some points we were doing the grating on the substrate, but also the grating on the active film. Okay, so we were doing, let me see this. When we were working with Techniker, we were fabricating the gratings with nanoprint lithography, either in CO2 with reactive ion etching, transferring to substrate, and also we did some studies printing directly in the polystyrene, which was the. And then in this case, with this particular work, we did one with 2 dimensions. Yeah. Normally, when you fabricate a 2D, normally the thresholds can be lower. I mean, if you compare, and there's been lots of work done in past comparing 1D versus 2D, normally the thresholds might be lower, but the point is that you don't get, so in this one, in the 1D, you get the emission maximizing the perpendicular direction. In the other, you can play with the angles of excitation and recollection. So in the end, the 1D is simpler, also simpler to optimize because of it's just this simple equation. And also for the purpose of sensing, for example, it's better because it's surface emitting. So
speculation. And I wonder whether you have changed the pumping power and whether you have observed how the height of the 2 peaks change changes. Maybe not. Haven't you changed the power of the pumping?
These two mean. Normally, when you do the experiment, you start pumping, and then at some point, well, you see this broad spectrum. Well, you see this spectrum. Well, it's not exactly the same because this one that I'm plotting here with the PL, this is taken from the fluorimeter. Okay. Normally, when you get it in the setup for characterizing the device, normally it's not exactly the same, but it's broad. But the point is that when you get at some point, you see a narrowing of the spectrum, and then I'm plotting the one at high end. And then when you have single ASE, it's the typical one, at some point you see a narrowing that starts in this peak. When you see dual ASE, normally you start seeing the narrowing, the two peaks at both. But maybe they don't appear exactly at the same pump, because to do this, you're changing the pumping. So you take one spectrum, then you increase the pumping, then you increase the pumping until you many spectra. And then normally, maybe this one appears first, and then very soon you see the other one. So you ended up seeing both at the same time. Sometimes it's true that maybe you see one, you continue pumping, and then at some point you start seeing the other one. So the thresholds are not the same. I don't know if this is here. I don't think it's here in this transparency. Well, it's not here, but the thresholds are not the same. Okay. And in fact, if here I'm plotting them, but you don't see, you see them at the same time only when you are a very high intensity. Normally this one appears first, if I don't remember. The threshold for this one, I think, is lower than this one, or the other, I don't remember something.
So this appears first when you increase the pumping.
Yeah, you start seeing the other one. Yeah. No, and the other one is, you see both. You see both. You keep seeing both. Yeah. But in fact, well, at the beginning, it was like a curiosity, like, oh, we see dual ASE. But in the end, this is a bad thing. Because the reason why you see dual ASE is because you have a loss mechanism in that area. So the thresholds are higher.
So you think that you have only one structure, and that structure produces two peaks?
In this case, yes. But there are some other people that have seen dual ASE with other molecules, for example, with PFO, with polymicrons. And they say that the observation of dual ASE is because they have like two different phases. So it's true that some materials, you can see dual ASE, but in this case, it seems that it's simply because you have, or at least for these molecules, it seems that there is an excited state absorption in this region. So in this region, the losses are quite high. So the threshold is higher. So because of that, you're able to see the other one.
If all the molecules would be exactly the same, it would either lace there or there, but not on both. So you must have some inhomogeneity, because this is homogeneous broadening. When one starts to lace, it takes the gain away from the other. So there must be some inhomogeneity to allow lacing on both positions. That some molecules have a different excited state absorption, slightly different than the others, or some other variation in the residual.
I think that is connected with the question of what is the origin of the excited state absorption.
Maybe.
If it's from the single molecule, I mean, it's excited state from the singlet, the molecule, or if there is some sort of intermolecular state that plays a role.
Is this, we don't know. We don't know. And in fact, well, we've seen this dual ASE in this compound, in this one, in the large one. We've seen that in the large one. Sorry. It's in this one. But also, I didn't put it here, but in this first study, when we published this paper, we published this, okay? But later, when we saw the dual ASE in the big one, in fact, we observed this in more detail, and in fact, there is a dual ASC also in this one, that we didn't see it at the beginning. Because the point is that, so we also see dual ASC in this one. And then, well, it's not in here, but we published another paper where in fact, that was the first one where we observed the dual ASC was in FCC3. And again, we saw this excited state absorption band in the PAMPRO experiment. And well, now lately, another thing that we're doing that is also connected to this dual ASC, which is something that we don't understand yet, is that with Perlin, which is a material that we've used for many years, what we have seen is that, I mean, normally you see with Perlin, you see, in fact, the spectrum is similar to this one. Okay, you have a mean PL peak, then first vibration, and then you see the ASC here. And it's always like that. But then what we observe, what we try to do is, okay, if we decrease the thickness of the film, normally the ASC occurs always at the same wavelength. But if you go to a film thickness that is very close to the threshold, to the cutoff thickness for the propagation of one mode, the ASC peak shifts to the blue. And then we thought, oh, maybe we are able to get emission in another peak, in the one that is supposed to be here or in the main peak, if we're forcing the thickness to be low, so this one cannot lace because the mode that this wavelength cannot propagate. So we have done that experiment, and we haven't published it yet because we still don't understand something. But we can see play with the thickness. We can see ASC either here or in the other one. You can change how you can change this just by playing with the thickness. But then we see, okay, we see this with the Perlin, but then we have tried to see this in other molecules to understand if this is supposed to be an effect of the thickness. But then we have done this with other Perlin molecules, and we see that. And I think we have seen also that with another kind of molecules, but there are other molecules where we don't see it. And in fact, Rafael is going to do hopefully some experiments, PAMPRO experiments, with the thickness, trying to see if we can understand this a little bit better. So yeah,
the object is to decrease the self absorption.
When you decrease the thickness, the point is that when you have a waveguide, in order to have one mode propagating in the waveguide, you have the minimum thickness that you need in order to have one mode propagate. When you have an asymmetric waveguide, that means when you have a substrate, film, and air. And then there's a cutoff thickness that for polystyrene over fused silica, normally this is 180 nanometers. So this is something years ago we tried to understand how the ASC behave with the thickness and the mode properties and all that. And then what you see is that ASC occurs always at a wavelength, but then when you decrease the thickness, at some point it moves to the blue. And this is because in this cutoff condition for the propagation of one mode, this cutoff condition depends on the refractive index, the thickness, and also the wavelength. So if you're decreasing the threshold, you say 180 nanometers, but this is for this wavelength. In fact, the cutoff condition is H over lambda cutoff. So for a given wavelength, you have a cutoff thickness, but then okay, if you decrease the thickness and then you cannot have propagation of that wavelength because the thickness is below, then what happens is that the emission moves to the blue. And then the idea was, okay, if we can force the emission to go to the blue, then maybe we're able to see emission, the ASC, but not just that is shifting because of this thing, but emission here. And we see that. But we see it in Berlin and not in others.
Okay. Is there more questions? Are there more questions? No? Okay. So thank you very much, Maria. We can continue talking.
Thank you.